And go ahead and share. You can see my screen.
Yes.
Thanks.
Don, you're muted. Sorry, Don, you're muted.
Okay, I'd like to thank everybody for showing up to our course on Principle of Quantum Networks. I want to introduce co-instructor Mateos Guedes de Andrade, who's a PhD student at UMass. I'm Don Towsley. I'm a professor at UMass. And we have a sort of a pretty intense let's say 3.5 hours in front of us, but I hope that you'll enjoy it. Uh, I'd like to start, first of all, with just asking what kind of background knowledge you have of quantum sciences, uh, and just to get a sense of where everybody is. I notice, Mateus, we have a polynomial decrease.
Oh, where? Oh, there's a. Oh, I see. Yes. There's a typo in the question, I guess.
Oops, and what happened?
Yeah, so I guess we got almost 80% uh, of coverage of
Okay,
the
so it
question.
looks like many of you have had exposure to quantum sort of principles of quantum sciences. I think it's not going to be a big deal because a lot of what we're going to be interested in is really sort of comparing and contrasting with classical networks. And so let me just quickly go through what we're going to do. I want to start off with a sort of a quick overview of quantum communications. And then we're going to spend some time, Mateus will start this, sort of comparing and contrasting classical and quantum networks. And after that, we're going to sort of dive into some of the issues that come up in quantum networks, scheduling, routing. We want to talk about an architecture referred to as a connectionless quantum network architecture, and then finish off looking at quantum network management and tomography. So just quickly, the purpose of a network is the following. When we have Alice and Bob, they have, let's say, quantum computers or quantum nodes some distance apart. Alice will prepare a quantum state, and we'll talk about that a little bit. And we'll want to be able to transfer it to Bob, so that in the end, Bob has this quantum state. So it's very much like classical communications, except that we're talking about quantum information. And the idea is that eventually we're going to have a quantum network that is going to be global in coverage. It's going to essentially connect millions, tens of millions, hundreds of millions of quantum nodes and allow them to do really sort of cool things. And so the key ingredient to this is something that's referred to as quantum entanglement. And in particular, there's a very special quantum entangled state called the Bell state that is we would like to have between Alice and Bob. And the Bell state is described as you see here. You can think of it that it contains sort of like two qubits or bits of information, one of which Alice has, one that Bob has, and with sort of special properties. I think of it as sort of analogous to, let's say that Alice has a coin, Bob has a second coin, and these coins, they're heads, tails, but there's an operation that Alice can sort of perform on it, let's say called a measurement. And when she does, she's going to generate either a head or a tail. And the special property that this entangled pair of coins has is that when Bob goes to do a measurement, he will produce the same result that Alice did. And in the case of a Bell state, each of these is with equal probability. And this is something that Einstein referred to as spooky action at a distance. It doesn't matter how far apart Alice and Bob are. This is what will occur. And it's worth noting that in 2022, the Nobel Prize in Physics essentially went to three physicists that really sort of explored this. Okay, so why are we interested in, let's say, a quantum internet? Al, we believe that it's going to be able to support a security as good as possible according to the laws of physics, and it'll be able to allow pairs or groups of users throughout the globe to be able to take advantage of it. It's going to allow the ability of having lots of small quantum computers be able to work together doing distributed quantum computation and be able to sort of break, let's say, web security and solve hard problems. It's also intended to be used for high resolution sensing, in particular, one of the targets being to be able to explore the universe. And then it's useful for transfer of quantum information. And that's something I want to talk about very soon. So let's go to this Bell state. As I said, think of it that you have in the quantum world two qubits of information. One is given to Alice, and the other is given to Bob, and it has a very special property that when Alice measures her qubit, she's either going to get a 0 or a 1. And if she gets a 0, then when Bob goes to measure his qubit, he's also going to get a 0. And if she measures a 1, then Bob will measure a 1. And this allows, for example, being able to generate shared randomness across distances, which is really perfect when you're trying to generate shared, let's say, security keys. And it's a key ingredient for lots and lots of different applications. And the one, uh, 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 there's an extension of this. I'm talking about it in the context of two qubits shared by two parties. There's something called the Greenberger-Horn-Zellinger or GHZ state that is essentially the equivalent, but that can be shared among n parties. And that's used in multi-party quantum key distribution, secret sharing, quantum sensing, quantum computing. And you can think of it in the coin example that I sort of showed before, is that three parties, let's say in this example, share three coins. And if one of them measures a head, then the other two will always measure heads. Okay, so I mentioned that one application is to what is referred to as quantum teleportation. Okay, and I'd like to just quickly go through this. We have Alice and Bob. Alice has a, a qubit of information, sort of like one bit of quantum information, and she would like to transfer it to Bob. And Alice and Bob share one of these Bell states that I was talking about. Well, the way that she can transfer it is as follows. She essentially entangles her part of the Bell pair with the quantum state that she wants to transfer, and then sort of does some measurements. The measurements produce classical information, let's say 1 and 0. Bob doesn't know anything about what's going on, but when he receives these two bits of information, then he can use them to determine what kind of operation to apply to his qubit. And the result will be that he will have that quantum state that Alice initially had. Okay, so with this in mind, I'd like to talk about fundamentals of quantum communications. And let's look at quantum comms over a link. So we have Alice, then we have Bob, and some sort of link between them. Could be a fiber optic link. It could be that it's just a line of sight free space link. Okay. The nodes have qubits, and what Alice will do if she wants to transfer something to Bob is she'll then essentially transfer her qubit to a photon, and the photon will be sent across to Bob. Okay, and that's referred to as one-way communication. So we have Alice preparing a qubit, let's say in some state, psi. She then transfers it to a photon, and the photon is then sent to Bob, and then Bob just loads the state into his memory. There's another kind of communication that has been explored that's referred to as two-way communication. And I'm going to show you sort of an example of it. We're going to add, I'll call it a Bell state analyzer to this link. And now what will happen is Alice and Bob will generate a photon memory Bell pair, transfer the photon to the Bell state analyzer. The Bell state analyzer will do measurements on those two photons and then send the results back to Alice and Bob. And if it succeeds, then Alice and Bob will share a Bell state. Okay. And if it doesn't, it's possible it might not. So there's some additional operations that need to be done to herald that indeed the Bell state exists. Okay, so why don't we have a quantum network already? Why are quantum communications so hard? And what the problem is that we have to deal with loss and noise. And so it turns out that what happens when Alice transfers quantum state to Bob, that the probability that it makes it to Bob decays exponentially in the distance between Alice and Bob. And so the rate at which Alice can transfer information to Bob decays exponentially with distance. And that's not the case with classical communications. The decay there is polynomial and much, much more gentle. So, question that we could ask in the classical world, we would, let's say, amplify the signal, okay? But the problem is that in the quantum world, there's what's referred to as the no cloning theorem that basically says you can't copy quantum signals, and so therefore you can't like just take it, make a copy, increase somehow its amplitude, and then send it. Okay, so this brings us to sort of a first poll question that I want to ask, and that is, how does the generation rate of, let's say, an EPR pair decay with distance in direct transmission through fiber? Is it a polynomial decrease, constant decrease, exponential decrease, or does it just depend on the fiber technology, or I don't know? And I'll give you, let's say, a few seconds to sort of mull this over. Okay, so looking at the results that we have here, I think most of you got it, that it turns out that the rate decreases exponentially uh, uh, in the length of the fiber between Alice and Bob. Okay, so let's continue on. So I've talked about loss, and now, as I said, noise is also a problem. And, and what it is qubits, unlike let's say classical bits, are not really, they're very sensitive to small perturbations. You'll encode, let's say, two classical bits, a 0 and a 1, and the encoding may deviate from, or sort of move away from what the true coding is. But if it doesn't go very far, you know where it should be. So here I have that the 0 and 1 have sort of moved away, but we know what it corresponds to. In the case of a qubit, it turns out a qubit has an uncountably infinite number of values that it can take. And so you could, let's say, encode a qubit as a 0 or a 1, and it could move away, but it will remain a valid quantum state. And so there isn't any way that you know that it's really sort of a noisy version of, let's say, a 0 or a 1, or whether that's actually what it should be. And then the other thing is that when you go to store, let's say, qubits in memory or do operations on them, uh, that can have a big effect. When you store in memory, it turns out that they have limited coherence times, and so you may end up storing a qubit, let's say that's a 1 in memory, and as time goes on, it essentially becomes sort of a superposition of 0 and 1, and eventually moves to 0. And so what happens is that in the communication example, let's say Alice communicating with Bob, noise can be introduced through the communications. The states will decohere. Bell states consist of 2 qubits, and so they have sort of twice the decoherence. And then, of course, you can have noisy gates and memory operations. And so if you take the one-way communication example, um, it may be that Alice prepared a state psi, and then what Bob gets is a 1 qubit mixed state row. In two-way communication, we've prepared a pure Bell state, but because of noise in the system, in the end, we have a 2 qubit mixed state. And so there's something called fidelity, which is a measure of the closeness between 2 quantum states. Uh, if the fidelity is 1, then the state you have is exactly what you wanted. And as fidelity decreases towards 0, then there's sort of a greater and greater difference between the state that you have and the state that you desired. And so in the case of a direct transmission, we're talking about sort of the fidelity of rho, or sort of the distance between it and what the state that Alice prepared. And with entanglement fidelity, it's really the difference between the mixed state of the 2 qubits we have and the Bell state. So now what I'd like to do is to talk about how we deal with loss and with noise. And the what has been proposed is introducing quantum repeaters. And so let's take Alice and Bob, and what we're going to do is we're going to place a repeater, a quantum node in between. Okay, and so that the distance now between pairs of nodes has been halved. And so in the one-way quantum repeater case, what Alice will do when she wants to send, let's say, state psi, is she'll use quantum error correction to protect it. We'll have an encoder that will do that. And then what will happen is that will translate into a whole bunch of photons that are entangled, that correspond to a code word associated with the state that Alice is sending. The repeater will get this, will decode, will correct, re-encode, and then transfer it to Bob. And so here, what we have now is we're never sort of vulnerable to photon loss across more than, let's say, a distance of L/2. And so we've significantly increased the probability that, let's say, the photons get across. Right, and there's a lot of work that's been going on in terms of like what are good error correction codes for this and appropriate for various distances. Okay, and one nice thing about this is that repeaters don't need to store information. On the other hand, they have to have very large and complicated circuits for doing the decoding and the encoding. There's something called a two-way quantum repeater, and the the foundation for this is to use quantum memories to store entanglement. So we have Alice and Bob, have repeater in the middle, and what we're going to do is we're going to store qubits there. And it operates in the following way. In phase one, each link generates link level entanglement or Bell state between the pairs of nodes across that link. Or let's say in this case, Alice in the repeater and Bob in the repeater. In phase two, the repeater does a Bell state measurement, and that has the effect of propagating the entanglement to the end. And the consequence is that you're now only vulnerable to photon loss across between pairs of nodes, and so the rate increases because of that. And so, in principle, what you could do is you could place lots of repeaters and sort of repeat this process across all of the links and at all of the repeaters and significantly increase the rate. Okay, I'd like to introduce another notion, multiplexing, and and it comes up because you can have, let's say, with a fiber optic link, you could be able to do things in parallel, let's say, across a whole bunch of wavelengths, just as an example. And so in the case of a one-way architecture, then you can think of it as that Alice generates a code word, and then it consists of, let's say, M qubits. They are mapped into M photons, let's say at M different wavelengths, and then sent across over in parallel to Bob. And so this turns out it's a bit like sort of multiplexing across the link. And so in two-way repeaters, what you would do is the following. You'd have, let's say, all these different modes or wavelengths, and in parallel, you would just generate or attempt to generate Bell pairs across all of them. Okay, and some would succeed and some won't. And so you could ask the question, well, what's the probability at least one survives, such that you could then use that for, let's say, a Bell swap. And it's very easy if you assume that losses are independent, then the probability of losses P, then you can write down the probability. You can also write down the probability that K of them survive. And in fact, it's given by binomial distribution. Okay, that brings us to the next poll question. How many EPR pairs can be generated in a multiplex attempt where M is the multiplexing number and P is the probability of one pair being generated? Is it half of the number? Is it M, the number of parallel channels times the probability of success? Only one? Or a random variable with a binomial distribution, or you don't know? Okay. Okay, so most of you thought that it was the number of parallel attempts times the probability of success. But it turns out that it's really a random number and that it can vary from attempt to attempt. And it turns out it's a random variable given with the binomial distribution. Okay, now I'd like to talk about dealing with noise. There's an operation referred to as entanglement distillation. And suppose that you have three bell pairs between, let's say, two nodes, and they have some fidelity F naught. It turns out that what distillation does is it performs some operations on these bell pairs, measures out all but one of the bell pairs, and uh, at the end, it will produce a, let's say, a single bell pair that will have a higher fidelity than was the case for the original bell pairs. And turns out there are lots of circuits for doing this. Here's a very simple one that will take two bell pairs, one called the source and the other called the target, and just performs a very simple operation at each of Alice and Bob called a C naught, measures off one of the bell pairs afterwards. They exchange communication, and if their measurement results are consistent, they know that they're left with a much higher quality bell pair. Okay, but it turns out it's probabilistic. And so if you remember, I talked about distillation fidelity being between 0 and 1. Distillation that I showed you before will succeed with a probability, let's say P sub S, and you'll get following kind of behavior. Suppose that two bell pairs have initial fidelity that I show on the x-axis here, then the blue curve essentially says what the final fidelity will be if it succeeds, and the red curve is the probability of success. And so, for example, if the initial fidelities were 0.7, you'll be successful a little under 60% of the time. But when you succeed, you're going to be left with a bell pair that's really much higher quality with a fidelity of 0.85. Okay, and so another poll question. What's the purpose of distillation? Is it to increase the bell pair generation rate, increase the fidelity, increase the distance over which we can do entanglement distribution? Or let's say, does it decrease fidelity so that we can get a higher generation rate? Okay, so most of you understood it right, and what it's there for is really to increase fidelity, but of course at the cost that you may decrease rate. Okay, so now let me just talk about a quantum network. So we've been sort of looking at sort of chains of these repeaters. A quantum network is going to include quantum switches with memories. They're going to be connected via lossy links. The links are going to be used to generate entanglement or to transmit quantum information directly. And the switches are going to be either measuring link level bell pairs so as to realize end-to-end entanglement, or if it's a one-way architecture, they will be decoding, encoding, and then forwarding quantum information. And so the challenges that we sort of face with, let's say, a quantum network is to decide what kind of service to provide. We've really sort of talked about two services. One is that you're generating an distributing entanglement, uh, and the other is that you're just going to directly transfer quantum information across the network. Other challenges, we have to deal with noise and loss. If this network is going to be useful, it's going to be supporting lots and lots of applications. And so there are questions of like, which applications do we serve? How do we allocate resources among them? What's the performance of the network? Questions come up in terms of, how do we manage this network? How do we measure its performance to see how it's doing? And you'll learn about tomography, which is one approach to doing this. And then there's the question of what should the data plane, what should the control plane look like? What sort of design? Okay. And so I'm going to stop here and I'm going to turn it over to Mateos, who is going to sort of start coverage of the topic of classical versus quantum networks.
Let me just share my screen. Yes, I guess you can all see the screen now, right?
Yes.
Oh, okay. Well, thank you, Don, for the introduction. And now I'm going to start discussing a little bit about the similarities and differences between classical and quantum networks. So to give you a brief outline, what we're going to see is an overview of the internet. And then we're going to discuss about network services and routing. And then finally, we're going to touch briefly upon the design of switches and routers. So what is the internet after all? It turns out that the internet is a network of networks that is loosely hierarchical and that is composed by the public internet, which is essentially the internet that we all have access to and that interconnects the whole globe, and also formed by private intranets that are private networks that enable the communication of users. So the internet is formed by protocols that will control the sending and the receiving of messages among the network users. Protocols such as the Transport Control Protocol, called TCP, the Internet Protocol, which is very famous, the IP protocol, the HTTP protocol that's utilized for us to browse the internet in web browsers, the real-time message protocol that is, for instance, the protocol that is used by Zoom to orchestrate real-time messaging. We have the Ethernet protocol, which works by providing addressing for machines, and the Wi-Fi protocol that governs how we perform wireless connections in our homes. The way that the internet is put together is via standards that appear in documents called RFCs, or requests for comments. And these documents are put together by the Internet Engineering Task Force, the IETF. Inside the IETF, there's a very interesting subgroup called the IRTF, the Internet Research Task Force, that thinks about how to innovate and come up with new protocols and implementations and standards for the internet. What is quite nice to see, Quantum Internet Research Group, which is, again, a group within IETF that is already thinking about how we're going to come up with standards for the quantum internet, even though we don't have full-fledged quantum networks already implemented. So now let's take a closer look at how the internet is structured, the network structure. We have the network edge, which contains applications and hosts. Mainly, we are part of the network edge. We interact with the network via the edge internet via the edge. We have the network core, which is formed by routers and is essentially what it is itself, a network of networks. And then we have access networks that can be either wired networks or wireless networks. So the network core is really formed by a mesh of interconnected routers. And there's a fundamental question that determines the architecture of a network. That is, do you perform circuit switching, which is a messaging approach that it's similar to how telephone networks used to work. You generate a circuit and performs distribution or you exchange messages via that circuit, or a packet switching network where the messages to be communicated are broken into chunks, discrete chunks, and these packets are what carry information among network users. So again, in circuit switching, we have end-to-end reservation of resources for end nodes. And the idea is that the network selects part of its link bandwidth and the switch capacity and allocates it to serve a particular communication request between end nodes. These allocated resources are not shared when other pairs of users attempt to communicate. And what is interesting is that this sort of reservation guarantees some sort of performance that resembles how telephone networks used to work. The problem with this approach is that really you need to perform a setup call. You need to inform the routers that users are communicating with each other and they must allocate resources in order to serve particular communication flows. On the packet switching view, the streams of data that are transmitted between end nodes are divided into packets. And the idea is that packets from different user pairs are going to share network resources. Each packet utilizes the full link bandwidth when it is transmitted, and it is an interesting way of sharing resources because you only use network resources as needed. Interestingly, packet switching brings us an interesting problem of resource contention, where since there's no reservation, no pre-allocation of resources, the aggregate demand that the users might have can exceed the amount of resource available. And this leads to interesting situations such as congestions. You can imagine that the routers in the internet have queues to store packets until they can be served through the links. And this can introduce congestions where packets will have to wait in routers to be transmitted. The fundamental property or behavior that enables packet switching to be successful is called store and forward. And the key idea is that the packets being transmitted will move one hop at a time. They will be, whenever a packet is transmitted over a link, it reaches a router and it stays on that router until it's time to be served. So let's look at a brief comparison between packet switching and circuit switching. Let's imagine that we have this router here and we have end users and we have an outgoing link from this router with 100 megabits per second capacity. Each user will, whenever it's active, will utilize 10 megabits per second or transmit information at a 10 megabits per second rate. And each user is active 10% of the time. If we perform circuit switching, where we allocate resources before communication starts, we can serve 10 users simultaneously through this outgoing link. In packet switching, though, if you have 35 users and you calculate the probability that more than 10 of these users are active, you have less than 0.004 probability of such an event occurring. And what this brings is, if you really use the sort of packet switching approach, you are able to allow for more users to simultaneously utilize your network. Okay, so now let's go over a poll question about packet switching. In packet switching, A, connection between endpoints is created before communication starts. B, users share the bandwidth of channels at every instant. C, the amount of bandwidth available is inversely proportional to the number of active users. D, packets use the entire bandwidth of the channel when transmitted. Or E, you don't know. Okay, I guess we have more than half responses, so maybe we can move on. The answer to this question is actually D. Whenever a packet utilizes a link, it will utilize the entire bandwidth of that channel to be transmitted. As a matter of fact, A, B, and C relate to circuit switching, where instead of where you have the sort of setup beforehand, where you ensure you fix the resources allocated to each user pair of the network before even performing or starting the flow of communication between them. Okay, so now let's go back at the structure of the internet, which is a network of networks that is roughly hierarchical. We have at the center of the internet tier 1 as ISPs, internet service providers, such as Verizon, Sprint, and AT&T. And the idea is that these tier 1 ISPs provide national and international coverage. And the tier 1 ISPs treat each other as equals, and they interconnect among themselves privately. Then we have tier 2 ISPs, which are smaller, often regional internet service providers that connect to tier 1 ISPs, possibly more than one tier 1 ISPs, and also can interconnect with other tier 2 ISPs. The idea is that these tier 2 ISPs will pay to tier 1 ISPs for connectivity with the rest of the internet. And in some sense, you can imagine that a tier 2 ISP is a customer of a tier 1 provider. And then finally, you have local ISPs, tier 3 ISPs. There are the last access to the network closest to or the users of the internet. And again, the tier 3 and local ISPs will utilize tier 2 ISPs, will be customers of tier 2 ISPs in order to be connected with the rest of the internet. And what is nice about the fact that the internet is a network of networks is that a packet that is transmitted between two endpoints actually traverses many different networks. And now I think this is a very important aspect to discuss, which is the internet protocol stack. Classical communication is not a simple problem to solve. And one way that engineers and scientists came up with in order to implement the full-fledged internet that we have today is to break its complexity into layers. And this here is the main standard division of the complexity of the internet into 5 layers that are where each one of the layers utilize the layer above uh, as a service to accomplish some particular or to obtain some different behavior. So we start at the highest layer possible, which is the application layer. That is the layer supporting network applications, such as emailing, copying files between different end nodes, and performing web browsing, for instance. And then underneath the application layer, we have the transport layer that deals with data transfer between two end hosts. And the protocols for this layer are mainly the Transport Control Protocol, TCP, and the UDP protocol. Then we have the network layer, which serves the transport layer, and it performs the routing of packets from source to destination. And the network layer is fundamental because it works as the glue of the internet. So the internet protocol, the IP, is essentially the network protocol that enables many of the different features of the internet that we have today. It is also the layer that must perform routing that uses routing protocols to compute the store and forward required data in order for packets to leave from point A and reach a point B in the network. Then after the network layer, we have the link layer, which focus on data transferring between neighboring network elements. And we have protocols such as PPP and the Ethernet protocol. And then finally, the link layer utilizes the physical layer, which is essentially the transmission of bits through wires or even wireless channels. And now that we saw the big picture of the classical internet and classical networks, we can start diving a little bit deeper into quantum networks. Again, remember that one of the reasons why quantum communications is so hard is because of the, exponential decay in fiber width distance. And we cannot simply utilize the same techniques that we had for classical information because the no cloning theorem precludes copying of quantum information. And then the way that we can beat this exponential decay is by utilizing quantum repeaters. And for now, let's focus on two-way quantum repeaters where we are trying to generate entanglement between different two end nodes. Again, remember that in the two-way communication that Don discussed with you before, we divide the entanglement generation process into two phases. The phase where we attempt to generate link level entanglement, in this case, entanglement between Alice and then repeater, and then entanglement between the repeater and Bob. And then once this repeater, these link level entanglement is generated, we can perform entanglement swapping to propagate the reach of entanglement and share entanglement between the end nodes. Nothing prevents us from inserting not one repeater between Alice and Bob, but multiple repeaters between Alice and Bob. And what is nice about increasing the number of repeaters is that by reducing the inter-repeater distance, meaning the distance between two repeaters, we actually increase the probability of generating entanglement between them. And then it's quite interesting to note that if we have actually infinite memory on the repeaters, we're actually able to achieve a generation rate, an entanglement generation rate that is distance independent, meaning it does not anymore depend on the distance between Alice and Bob, the two end nodes. Unfortunately, this property is broken down whenever we don't have infinite memory, right? And in fact, we live in a finite world, so we are restricted to utilize only finite memories. But then again, whenever we lose this property, we get back to scaling that depends on distance. And if we have only one memory, unfortunately, we go back to the exponential decay to generate entanglement as we had before. And the way that in a similar way that we divided the complexity of the classical internet into layers, we can do a similar thing on the quantum internet. And what we see here is an attempt to come up with a layered structure for the quantum internet that matches the layered structure of the classical internet. And just note that this is not a standard yet, or we don't even know if this is going to come up to be the actual standard, but still is more of a tool that we can use to think about and to design quantum networks. In a similar way that the application layer supports classical applications for the classical internet, the application layer would support quantum applications over the quantum internet. And then we might have a transport layer that will again perform host to host quantum data transfer. And we can think about protocols that will generalize, let's say, TCP and UDP to the quantum scenario, let's say the quantum TCP or the quantum UDP protocol. And then this transport layer would make use of the network layer that itself would have the purpose of generating entanglement between end nodes. And then in this layer, we would have protocols such as the quantum internet protocol and protocols to perform path selection in order to generate end-to-end entanglement between end nodes. Then we reach the link layer, which would perform link level entanglement generation, let's say the generation of entanglement between repeaters. And then finally, the physical layer would deal with photons on the wire. One very fundamental aspect of the classical internet is the ability to perform reliable communications. We also have errors in classical communications, such as bit flips and erasures. And whenever we introduce packet switching, we might also have problems such as dropping packets. That this could be caused, for instance, by congestion. It might be the case that the internet is being overutilized or the network is being overutilized. And then whenever a packet is transmitted from one router to another router, the receiving router does not have enough space in its memory to store the classical information to be transmitted. And the way that we overcame such problems was with recovery schemes. For instance, utilizing error detection and correction codes for errors such as bit flips and erasures. And in terms of dropped packets, the way that the internet decided to, or the way that the internet implements reliable communications against packet dropping packets is packet retransmission. Note that this sort of packet retransmission relies on cloning, which unfortunately, so if we want to do packet retransmission in quantum, we need to have different ways to implement that. So to give you an example of how we can perform reliable communications over a classical network, we might have our sender and receiver, and that sender sends a packet 0 to the receiver. Whenever the receives that packet, it replies to the sender with an acknowledge message saying that it received packet 0. Then the sender sends again packet 1, and then let's imagine that packet 1 gets lost as it is being propagated through the network. The sender has a timeout that whenever it starts a clock when it sends the packet, and whenever that the time it takes, it waits for a response surpasses a given threshold, it understands that the packet was lost in the network. And then it simply resends the packet until it receives an acknowledgement. So in quantum, performing reliable communications is slightly trickier. Well, we have errors introduced in many different parts of quantum communication, and this is a non-exhaustive list of errors that occur in quantum networks. For instance, we have many different channels that describe how qubits accrue error, such as Pauli channels, eraser channels, and the amplitude damping channels. We have gate noise, that is essentially the noise introduced by performing quantum operations. We have memory decoherence, which is the noise that qubits accrue when they're being stored in memory. We have transduction noise, for instance, when we have to transduce information stored in a qubit to a photon. We have loss in optical components. We have problems of catching photons on receivers. And also, we have probabilistic operations that can cause the loss of states being transmitted. And then the recovery schemes that we can utilize to overcome these errors are quantum error correction. For instance, this is essentially the scheme utilized in one way. We can perform distillation to increase fidelity of the states being generated or qubits being transmitted. We can perform data retransmission in one way, where here, given that we cannot copy information, the source that is sending qubits must regenerate the qubits in some sense, somehow. And then in two-way, we can perform attempt and to succeed to overcome failures. And you can think that this procedure of attempting until you succeed, meaning you keep performing generation attempts until you see entanglement generated, works like a two-way retransmission. Again, recall that not only we have the problem of exponential loss, we also have the problem of noise, and that we have the qubits are not protected against small perturbations in its states, and also that the memories we utilize cannot keep information forever. And what this leads us to is actually that when we are utilizing a network to generate entanglement or to distribute quantum states, to generate entanglement, we might have imperfect entangled states generated between Alice and Bob, and even in between quantum repeaters. So now let's look at this case where we have Alice, Bob, and then a repeater in between. And then if the world was perfect, we could generate a perfect Bell state between Alice and the repeater and a perfect Bell state between the repeater and Bob. Unfortunately, all the noise introduced through communications and decoherence will prevent us from seeing this idealized scenario in the real world. What we have is actually, whenever we perform link level entanglement generation, we have a state that looks like an imperfect Bell state between Alice and the repeater, and then the repeater and Bob. And we can again quantify how good the states that we generated were based on the fidelity, which is again a metric of how close two quantum states are. Once more, recall that entanglement fidelity is the fidelity between the states that were generated in the links, through the links, with a perfect Bell state. In this case, 0, 0 plus 1, 1. And again, we can overcome problems such as loss and infidelities or errors and imperfections utilizing multiplexing. And when we put all of these things together, we have repeater networks that have access to multiple memories, and they can perform multiplexed attempts to generate link level entanglement. So again, multiplexing is nothing more than the parallel generation of entangled states between repeaters. And since we performing multiple attempts in parallel to generate entanglement, we can increase the rate of entanglement generation between end nodes. Also, since we have multiple entangled states between repeaters, we have an opportunity to perform distillation and pump up the fidelity of the entanglement that we are generating. So imagine that we have Alice and Bob and many repeaters interconnecting them, and then that whenever we can successfully generate an entangled state between two repeaters, let's say in this case repeaters R1 and R2, the state that we generate has a fidelity F0. If we have multiple states generated between repeaters, we can distill them together and obtain states that have higher fidelity. What is nice about this is that imagine that we have multiple states generated not only between neighboring repeaters, but let's say Alice and R2, and then R2 and R3. What we can do is this notion of multi-hop distillation, where we not only distill entangled states that are that were generated between neighboring nodes, but entangled states that are generated between nodes that are two or more hops away from each other. For instance, we could perform distillation between entanglement generated between Alice and R2. And then there are interesting questions here. For instance, we would like to determine, whenever we're implementing a two-way multiplex repeater chain, determine when and how much should we distill? How many pairs should we utilize for distillation? And which type of distillation, multi-hop distillation, should we use? Maybe we don't even need to use multi-hop distillation. We can just do link level distillation, so on and so forth. And another interesting aspect of this is we could come up with ways to try to distribute entanglement between Alice and Bob with a possibly fidelity constraint or a fidelity threshold. In the sense that we are going to attempt to generate entanglement between Alice and Bob with a fidelity F prime that is good enough for different applications. And this essentially, I guess, closes up how we can perform reliable communications between Alice and Bob, let's say, in a two-way network. So now let's go back at the classical view and look at the functionalities implemented by the network layer. Again, the network layer serves to transport packets from sender to receiver, and the network layer protocols will run on every host of the internet and every router of the internet. And there are three key functions implemented here. The first is path selection. Essentially, the network layer needs to come up with routes that will be taken by packets connecting source to destination, and this is performed via routing algorithms. We have switching, which is how do we move a packet from an input port of a router to an output port. And if we are performing architectures that somehow resemble circuit switching, we might also need to perform a call setup procedure to allocate resources on paths interconnecting two end nodes to serve data flows before sender and receiver communicate. Okay, so this is just a delayed animation. But then whenever we are designing classical networks, we really need to decide which service model that network will implement. Would we have a guarantee bandwidth for communication between end nodes when they communicate? Do we have some sort of a preservation of the interpacket timing? For instance, implementing a no jitter service? Can we have a delivery of packets or of information that is loss-free? Can we have a delivery of information that follows an ordering? For instance, if you send packet 1 and 2, packet 1 arrives first in packet 2. Do we implement congestion feedback to the sender to try to prevent congestion events of occurring in the network? And essentially, the crucial question is, what is the network layer implementing? Is the abstraction providing virtual circuits or providing datagram exchange? And here I'm going to stop, and Don will start talking about virtual circuits with you.
Thank you, Mateus. Right, so I'm going to start with virtual circuits, and we'll talk a little bit about sort of counterpart and quantum networks. So the idea with the virtual circuit is that, okay, you have this packet switch network, but you want the source to destination path to behave as if it were a telephone circuit, um, performance-wise. Okay, and so, what
Sorry,
that
Don.
means is,
Don,
oh,
excuse me. We're not seeing the screen.
oh, you're not. Sorry, apologies. Okay, now you are. Okay, so what we want is in a virtual circuit is that the source to destination path behaves like a telephone circuit. And so, as you would expect, you would have a call setup. You would have a call teardown associated with each call, let's say before the data can flow and after you're done. Each packet would have to carry some kind of virtual circuit identifier, which would not necessarily be the destination host ID. An important thing is that each router on the source destination path is going to have to maintain state for each passing connection. Okay. And the router may allocate resources, bandwidth on the links, buffers to the virtual circuit in order that you really can get a virtual circuit-like performance. And so just sort of showing a animation of what that might look like is you'd initiate a call between the two end nodes. The receiving end node would then essentially accept the call. And once that was done, the initiating node would know that the call was connected. And what it would do is then just start to send data. It would go across a very specific path to the receiving node where it would be received. The other service that Mateos mentioned is sort of a datagram service, and that is really what the internet model is. And in this case, there's no call set up at the network layer. Okay. TCP is a transport layer protocol, and it does do call setup, but it's above the network layer. And so the routers don't have any state about end-to-end connections. There's just no concept of a connection in the network. And in the internet, packets are typically routed according to the destination host address. Okay, and that's how the routers can get by not really knowing what flows packets belong to. And furthermore, packets between the same source destination pair can take different paths. So the animation is the sending host sends data. It goes through the network in some way or another, and the receiving node receives it. And that's all there is to it. So if we look at, let's say, the quantum network and what the service model might be there, what would we want? Would we want, let's say, guaranteed rate, latency guarantees, minimum fidelity guarantees? And at least at the network layer, is either that it's generating entanglement and distributing to the end hosts that want it, or that the network is just being used to transmit quantum information. And so I want to look at each of those in turn. Let's start with the two-way network architecture, and we saw this earlier, but the idea is that the network is really just creating and distributing belt pairs. And as you recall, if you recall, it generates them at the link level, and then it does measurements at the repeaters or switches that then propagate the bell pairs to the end nodes. And if there's a need to transfer quantum information, then the end nodes can use teleportation to do that. And it relies heavily on distillation then to handle noise, distilling the bell pairs either at the link level or across segments of consisting of multiple links. And it requires an exchange of classical information in order to make corrections based on what the measurement results are when you do the bell state measurements. And so that brings us to the next poll question. And I want to ask you about quantum teleportation and sort of see if you've sort of been paying attention. What is its purpose? Is it to correct errors when distributing bell states to users? That's A. Or is it to transport classical information from one user to another through the expenditure of a bell state? Or is it used to transport quantum information from one user to another through the expenditure of a bell state? Or D, is it used to transport a human being from a spaceship to a planet? And E is I don't know. Okay, so it most of you have it right. Is if you recall, it's really to transport quantum information between users through the expenditure of a bell state. It turns out, although we haven't talked about it, there are other protocols that can be used to transport classical information through the expenditure of bell states, but that's not what quantum teleportation is. Okay, so now let me just quickly go over one-way network architecture, which we talked about before. And basically, it's really to transfer quantum information directly. And let's say Alice has prepared a state psi naught, and then it just transfers it through a path, across a path to Bob. And, it's interesting to note the resemblance to a classical network. It doesn't look very, very different. And so one expects that one ought to be able to borrow a lot from classical networks. It relies heavily on quantum error correction. But on the other hand, one benefit is it doesn't require exchange of classical information. Now, it turns out that the quantum networking community has been focusing primarily on two-way network architectures because the belief is that the challenge of being able to do quantum error correction is such that it's going to be years before we're going to be able to build repeaters with that capability. Whereas with a two-way network architecture, it's much easier to do distillation. And so you'll sort of notice as we go through the rest of the course that, much of our focus is primarily on two-way network architectures. But one thing to point out is if you have a network that does one, well, you can do the other. We talked about with two-way architectures, you can teleport quantum state from one node to another, and there's nothing to preclude you in the one-way case that Alice generates a bell pair and then just transfers one of the qubits to Bob. Okay, so what might the quantum internet look like? Well, we sort of expect that what you're going to have is, again, lots of networks, just like the classical network, and that the quantum information will pass through uh, many networks, and uh, or you'll be generating end-to-end entanglement across many networks. One of the challenges here is that you're going to have some, let's say, internet service providers that will have an architecture used to distribute entanglement, while others are going to be, let's say, designed to transmit quantum information. And they will also be using different kinds of technologies. And so that will poses a really interesting problem of how we're going to be able to truly interconnect quantum nodes in such a network. Okay, so just to sort of summarize one-way versus two-way, starting with two-way, the pros are that distillation is much simpler than quantum error correction. Another advantage is that what you're doing is you're always generating and distributing bell pairs. And so, nice thing about that, bell pairs are fungible. You don't care which bell pair you get. And so that allows for the possibility of generating at very high rates. You can also pre-share bell pairs ahead of time. You could store them in some third party infrastructure. And because distillation is simpler than quantum error correction, you can tolerate noisy gates. The cons is that you have to do two-way classical communication, and that can increase latency. And you have to have the ability to store qubits in the repeaters while you're waiting for link level bell pairs to get created. If we look at one way, pros are that uh, you don't have any classical comms that decreases latency. You have very low memory requirements because you're not waiting, let's say, for both links to sort of complete something. And so it allows for pre-sharing of entanglement. The cons are that quantum error correction is very challenging and requires high quality gates. And we're talking about codes that could number really in hundreds of physical qubits to encode a single logical qubit. And because it's you have to deal with loss, you don't have this fungibility here. It may require many more quantum repeaters than a two-way quantum network. Okay, so brings us to the next poll question, which is, what are the advantages of a two-way quantum network architecture? And here, select all the ones that apply. A, tolerates noisy gates. B, it introduces latency due to the need for classical communications. It requires considerable quantum memory. It can provide high rates, or you're not sure. Okay, we'll wait till some more people have. Okay, I'm going to end the poll. And it turns out that one advantage is that it tolerates noisy quantum gates. And the other is that it can provide high rates because of the fungibility of these bell pairs. The other two are certainly properties of two-way quantum communication, but not desirable properties. We don't want to increase latency, and we would prefer to have a setting where we could get by with fewer quantum memories. Okay, now I'd like to talk about routing. And the notion here is we have a network, and the goal is we want to determine a good path, let's say, through the network from the source to destination. Let's say if A is the source and F is the destination, we'd like to find a path. And the way that this is typically handled is to think of it as a graph theoretic problem where the nodes in the graph are routers, the channels or the links between routers are represented by graph edges, and to associate costs with the links. Could be delay, it could be some monetary costs, it could be a level of congestion. And then selecting a good path typically means, let's say, finding the minimum cost path, although other definitions are possible. And Dijkstra's algorithm for solving for shortest paths is very a standard algorithm that's used in the classical internet. Now, I'd like to talk about classifying routing algorithms, let's say for the internet. One question is, do you have, let's say, global information that can be used to generate the paths, or do you try to generate paths using decentralized information? By global, typically what you would have is a central controller that has the complete topology and has all the cost information. A decentralized approach might have routers that know who their neighbors are, knows what the link costs are to the neighbors, and then all of the routers run some sort of distributed algorithm, sort of an iterative computation, where they exchange information with their neighbors and eventually converge to the best routes. And these are typically referred to as distance vector algorithms. Another question to ask about routing algorithms are they static or dynamic? By static, I mean that the routes that are computed are put in place for a long time and only very slowly are changed. A dynamic routing algorithm would have the routes changing much more quickly, let's say perhaps due to periodic updates or perhaps in response to link cost changes. And I'll just say the current approach is that to have a central controller that has all of the information, okay? It may be that the central controller is sort of deployed in sort of a distributed manner, but that's the basic idea. And one thing that's worth noting is that routing algorithms also include policy constraints, like a network A may not be allowed to use, let's say, links in network B because of either financial reasons or whatnot. Another thing that, let's say, the current internet routing algorithms are concerned about is calculating backup paths so that they can react very quickly to failure and to introduce diversity so for the purpose of balancing loads throughout the network. Okay, so just very briefly with quantum routing, what has been done to date is there's been a lot of work on sort of like trying to develop static algorithms, which typically are shortest paths where with, let's say, different kinds of link costs. Some of them would be that you essentially have a cost associated with the link entanglement rate. Others will, let's say, take fidelity into account. And there's just a lot of work that's been done here. And the community has also been looking at dynamic algorithms where the nodes, the quantum repeaters, choose their neighbors to connect based on local state information. I want to talk a little bit about routers. And just a very quick overview of a classical router. There are really two functions of the router. One is, of course, it runs the routing algorithm or the protocol associated with it. The other is that it needs to forward packets from an incoming link to an outgoing link. And so there's a lot of work that's been done. There are all sorts of interesting questions that arise. For example, what's the capacity of the router? What should the switch fabric look like? What kind of scheduling policies should one use, and can they achieve the router capacity? And you would like to do it in a way that it makes the switching fabric simple. And I'll just mention that the community has looked at matching algorithms, max weight policies, lightweight randomized algorithms for sort of handling these questions. Okay, in the quantum realm, we've been talking a bit about quantum switches. A one-way quantum switch would look much like a classical router, so I'm just going to talk about a two-way quantum switch. It includes memories for loading from the links and reading out, the capability of doing quantum measurements. It has to be able to perform some quantum logic. Bell state measurements and distillation require quantum operations. They tend to have multi-photon entanglement sources. That's needed especially for the purpose of many operations require the use of ancilla qubits. And so that's what they would do. And then, of course, the capability of doing classical processing and communications. And just sort of very briefly looking at the quantum switch and how it operates. Okay, user pairs will be generating requests for bell pairs. And so, as we saw before, in the first phase, links will randomly generate bell pairs, which I'm sort of showing here. And then in the second phase, given the outstanding requests for end-to-end entanglement, the switch has to select the bell pairs to measure. And it turns out that that's equivalent to selecting an eligible matching in a graph among memories. Think of it that these red nodes are essentially qubits belonging to link level bell pairs, that the edges between them indicate requests that would like to be able to do bell state measurements across those pairs. And then in the end, you do sort of a graph matching. And then that determines the bell state measurements that you do. Okay, so we're at the end of sort of this comparison of classical and quantum, and I just want to mention some of the challenges, and then we'll stop for a 5-minute break. So it's still unclear what the design of the switch, what the right switching fabric should be, what kind of teleportation. For example, in some proposals, the thought has been that you would teleport across between interfaces. There's also questions of like, how do you determine the capacity of the switches, of the networks? How do you do resource allocation? Do you use global state information or local state information? At what time scale should this be operating at? What's the effect of memory decoherence, gate errors? What's the quality of the information that in the end, in terms of fidelity? And of course, we know that fidelity degrades over time. And I'll just mention that, like you probably have sort of seen that maybe if you want to do end-to-end bell pair generation, that it might make sense to do something that looks like virtual circuit switching. And something that comes up in the context of, let's say, resource allocation is that if you have a bunch of bell pairs and some of them have lower fidelity than others, or they're older, they've had more chance of decohere, should you account for that when you, let's say, schedule bell pairs or select bell pairs for doing bell state measurements? Okay, and so last slide for this section is that entanglement distribution that you should sort of see is really very different from quantum information transfer. And I hope that you have certainly seen that quantum networking introduces new problems, but that it seems like we can borrow some ideas from the classical internet. Okay, and then again, lots of interesting questions regarding resource allocation, path selection, scheduling, and how to deliver quality of service in a very noisy environment. Okay, so let's stop here and let's take a break and reconvene. My local time is 12:40, so I guess let's say 20 minutes before the hour.
In the meanwhile, I'll keep answering questions in the chat.
Okay, and I guess you are up next.
Yes.
I left a couple of questions for you because I thought you might be better able to answer.
I already did them. I have some newer ones.
So,
For some reason, I cannot type anymore on the.
oh, I see. There are a bunch of outstanding questions still, right?
Yeah.
I answered the first question. Somebody else asked, and I gave an answer. I'll see if I can find it.
Mhm. Oh, Don, I think we are, you said 20 minutes before the hour?
Yeah, yeah. So I think you should go ahead and start.
Okay, I'm just gonna share my screen. Oops. Yes, I guess you can all see my screen already. So what we're gonna talk about now is scheduling in quantum repeater chains. And in particular, what we're gonna do is focus on a two-way quantum network. And the way that the distribution of entanglement works on a chain, essentially the question that we want to address is how are we going to generate entanglement between the end nodes of our repeater chain? And in particular, when should we generate link level entanglement between neighboring nodes? And how should we perform entanglement swapping with entanglement that was with link level entanglement? So the first fundamental property that we have here is that swaps commute. Let's imagine now that we have this repeater chain here where we have links, entangled states generated between each and every repeater, shown here by these purple lines. And each one of the distance between repeaters is just denoted as L sub I. So again, we are in a scenario where we assume that all the link level entanglement in the network was generated. The operations of Bell state measurements of our entanglement swapping that are to be performed at each one of the repeaters commute with each other in the sense that any ordering that you select to perform these swapping operations will give you the same end-to-end state, meaning the entangled state distributed between Alice and Bob. And what is also nice about this commutability of swap operations is that not only you can perform them in any order you want, you can, in principle, perform all of them at the same time in parallel and still generate end-to-end entanglement between Alice and Bob. Nonetheless, the ordering that you select to perform entanglement swapping will impact the performance, and it has consequences for the design of network architecture and network protocols. What we're going to see today is three different entanglement swapping policies: sequential swap, swap as soon as possible, and nested swap. We're going to assume for now that our entanglement swapping operations are all deterministic, and we're going to start by looking at sequential swaps. So again, we are in a scenario of a quantum repeater chain, and what the procedure that we're going to do is as follows. Alice will start link level entanglement generation with the first repeater R0. And let's imagine that the generation of this entangled state between Alice and the repeater takes a time t0. Once this entanglement generation succeeds, the repeater R0 will then start link level entanglement generation with R1. Again, the link level entanglement generation process is probabilistic, and it will take some time, T1, for this state between repeater 0 and repeater 1 to be generated. Whenever this state is indeed generated, the repeater 0 will perform a Bell state measurement or an entanglement swapping operation, generating now entanglement between A and R1. And we can assume that the time it takes for R0 to implement or to perform a Bell state measurement is negligible, such that the total time that it takes to generate entanglement between Alice and R1 is T0 plus T1. Then the repeaters in the chain will repeat this process until entanglement is generated between Alice and Bob. Now Alice shares entanglement with R1. R1 will start the procedure to generate link level entanglement with R2. That's going to take an additional time T2. Then whenever that state is generated, repeater R1 performs an entanglement swapping operation between these two qubits here in the figure, generating entanglement now between A and R2. And this process took a total time of T0 plus T1 plus T2. Again, the same is true for repeater 2 and B. It takes a time T3 to generate link level entanglement. We perform a Bell state measurement operation, and finally we generate entanglement between A and B. At the end of the day, the latency that it takes us to generate entanglement between Alice and Bob is, in this case, the sum of the time it took to generate each link level entanglement in the chain. When we look at a generic chain of n repeaters, this latency is linear in the number of repeaters that we have, meaning that we simply need to sum the time it takes to generate link level entanglement at each link in the chain. Now let's go over a quick poll question. What is the end-to-end entanglement generation latency when sequential swap is performed? A, it takes constant time, meaning does not depend on how many hops we have in our chain. B, it's linear order of n in the chain with respect to the number of nodes in the chain. Is it n squared? Is it log n, or you don't know? Okay, let's wait a little more so that we have at least 50% coverage. Okay, I guess then maybe we can proceed. So the actual answer is the generation is linear. This latency is linear with respect to the number of nodes in the chain. Okay, so let me just move this down. Our second policy for entanglement swapping is swap ASAP. Again, we have a repeater chain, but now, we're going to perform link level entanglement generation at every link simultaneously. And then whenever two links are available, we're going to perform entanglement swapping. So let's see an example. Again, imagine that we are attempting to generate link level entanglement between every repeater in this chain. And let's say that after a time t0, the first entangled state that is successfully generated is the state between R1 and R2. Since we only have one entangled state here, we cannot perform entanglement swapping, and the process goes on. Now, let's say at time t1, we have created a state between A and R0, and now, again, we cannot perform entanglement swapping because there is no repeater that has entanglement on both of its ends. Then we wait for some more time t2, and we generate entanglement between repeaters R0 and R1. Now, in this scenario, we can actually perform two entanglement swapping operations in parallel. We can perform the entanglement swapping at R0 and an entanglement swapping at R1 in parallel. And then generate an entangled state now between A and R2. And note here that the time to generate T2, the time generated entanglement between R0 and R1 was greater than the time T1 or equal to, and then T1 itself was greater than or equal to time T0. And then again, we simply repeat this process until we generate end-to-end entanglement between A and B. So after time T2, we generate an entanglement between A and R2, and then we need to wait for some more time until the link level entanglement between the repeater 2 and B is successfully generated. Whenever that is the case, we perform a Bell state measurement in R2, generating an unentangled state between A and B. And it turns out that if you utilize this policy, the latency that you have scales with log n, where n, again, is the number of repeaters in our chain. So let's go over another quick poll question. That is, what is the end-to-end entanglement generation latency when we actually perform swap ASAP in a quantum repeater chain? A, constant. B, linear with respect to the number of links. C, quadratic with respect to the number of links. Or D, a logarithmic with respect to the number of links. Okay, I guess we got more than 50% coverage. So now we can see the result or the answer. Guess most of you got it right. The latency in this case is log of n, where n is the number of repeaters in the chain. And just as a quick recap, when we used the linear generation, or the sequential schedule, we had a linear relationship between latency and the number of repeaters. Okay, the final swap policy we'll see today is the nested entanglement swapping policy. Here, what we're going to do is, again, we're going to assume that we perform link level entanglement generation in parallel for all links in the same way that we did with swap ASAP, but we're going to focus on finding a midpoint between Alice and B, which is in this case repeater 4, R4. And then we're only going to perform entanglement swapping in R4 when we have entanglement between A and R4 generated, and then between R4 and B generated. And then we're going to repeat this process until it's possible. So we reached R4, then we're going to look at a midpoint between Alice and R4, which is repeater 2, R2. And then in R2, we're only going to perform entanglement swapping whenever we have a link between A and R2 and a link between R2 and 4. Okay, so now let's look at R4. Here is the midpoint of the chain. Then the second midpoint is R2 and R6. The second midpoints are R2 and R6, respectively. And then the third ones are R1, R3, R5, and R7. And then the ordering that we do entanglement swapping is as follows. We're going to perform first entanglement swapping in R1, 3, 5, and 7. Then entanglement swapping in R2 and R5. And then finally entanglement swapping in R4. So the whole process goes a little bit like this. We first generate link level entanglement between the repeaters we're attempting in parallel, and then we can perform swaps at R1, R3, R5, and R7. And whenever these succeed, now we have shared entanglement between A and R2, R2 and R4, R4 and R6, R6 and B. We repeat again the entanglement swapping at these nodes, finally generating entanglement between A and R4, and then R4 and B. And with an additional Bell state measurement operation performed in R4, we generate the end-to-end entanglement between Alice and Bob. So let's go over a quick analysis on these three different policies. Well, each of these swap schedules will have different performance. And if you consider that you have a probability Q to succeed when you're performing entanglement swapping, meaning if we break the assumption that entanglement swapping is deterministic, the rate of generating entanglement changes drastically. In some sense, sequential is simpler to implement than the other swapping policies because it follows classical networking, where we do sequential store and forwarding, if you recall from our last section. Nonetheless, you can still implement swap ASAP and nested, but they will require some additional control when compared to performing sequential swapping. So let's see a table that summarizes a little bit of the properties of these three different policies. The probability of generating an entangled state between n nodes when you're performing sequential is q to the n, assuming that we have the probabilistic entanglement swapping. With swap ASAP is also q to the n, but when you perform a nested policy, actually the probability that you're going to generate end-to-end entanglement is q to the log n, where remember q is the probability that you're going to be successful when performing an entanglement swapping. Another interesting metric is how many Bell pairs are simultaneously decohering the chain when you are performing your end-to-end entanglement distribution or generation. When you do sequential, you only have one pair at a time in the chain decohering, but then for swap ASAP and nested, you may have multiple Bell pairs decohering simultaneously until you are able to generate end-to-end entanglement. And finally, the latency, when you're considering deterministic swaps, is linear for sequential and logarithmic for both ASAP and nested. Then the final thing to discuss is how noise affects distribution. What happens when we have imperfect entanglement being generated via the network links? If you assume a worst case scenario where the noise corrupting the states is depolarizing noise, let's say that we have an entangled state generated between 0 and 1, and then 1 and 2, and then each one of these states has a fidelity f0. In the case of depolarizing noise, the rule that tells you what is the fidelity you obtain between 0 and 2 when you perform swapping in 1 is that this end-to-end fidelity is the product of the individual fidelities. And since we are assuming that we have noise, we see that the end-to-end fidelity is smaller than the individual fidelities that were concerning the states that were generated between the neighboring nodes. And what this brings to the table is that the noise accumulates exponentially with the number of repeaters because you're multiplying fidelities to calculate the end-to-end fidelity. This means that if you really want to have a useful entanglement being distributed, we'll need to consider distillation once we start adding multiple repeaters in between and nodes. Again, here, the different policies that I showed you exhibit very different performance with respect to the fidelity of the states being generated, although I'm not going to dive deeper into how these different distillation, these different policies will affect distillation. And now I'm gonna, I guess Don is gonna talk to you about quantum network routing.
Okay, thank you, Mateus. Oh, sorry, I just realized I have the wrong slideshow mode. So let me fix this. Apologies. Okay, so what I want to do now is to talk a little bit about routing in quantum network. And first of all, let's just talk about the routing problem in general, both classical and network. We're given some network represented by a graph, a set of vertices and edges. And what we want to do is really find a path between, let's say, pairs of nodes that we can perform entanglement. So how is this solved in the classical world? Well, it depends if we're doing circuit switching or virtual circuit switching rather than just packet switching. Uh, and so for simplicity, let's just focus on finding paths. Okay, and as I sort of talked about before, we'll assume that centralized controller knows the topology, it runs the shortest path algorithm and passes the route information to the routers that populate their tables with forwarding information. Okay, and so we have a router R naught, and it will have, let's say, incoming packets that might have, let's say, a destination address. Let's say the destination address is A, and the table would just say which neighbor to send that packet. Or if it's sort of a virtual circuit, uh, uh, then we would have a flow ID associated with the virtual circuit, and the table would be populated with the flow IDs. Flow ID A would have its packets routed to, let's say, R1. Okay, so how about two-way networks? You can sort of see that a one-way network, you ought to be able to do something very similar. So do two-way networks differ? And one thing that in what we're going to talk about is we have this network here, and the links here represent channels over which we can generate entanglement. Okay, and if we want to connect two end nodes, let's say, and allow them to generate entanglement, we're going to have to require generating link level entanglement. And as we've made pretty clear, this is a probabilistic process. Okay, so let's say we have A and B, they want to generate entanglement. And so we could sort of follow what's done classically. Controller could find a path P. And then once you have the path, you can use one of the three swap scheduling policies that Mateos talked about to generate end-to-end entanglement. And you can repeat this until this process of generating link level entanglement until you finally successfully generate entanglement between A and B. And if A and B need multiple bell pairs, you continue this process. And so methods work, although there's a question about how much time is required to be able to generate the end-to-end entanglement. And there's a question that comes up here. What I've done here is sort of present it as if it's sort of a bit like circuit switching. You select the path, and once you have the path selected, then you attempt to generate entanglement between end nodes. And so an interesting question that comes up is there something that might be analogous to packet switching? And that's really one of the things that we'll explore. So I'd like to do a back of the envelope analysis. And we're going to assume the two-phase time-slotted model. Okay, phase one, you generate link level entanglement, and then in the second phase, you swap. And we're going to look at a case where memories are fragile, that the qubits can only last one time slot. Okay. And in that case, if in the case of sort of like a linear repeater chain, the rate will decay exponentially with distance. In order to be able to get sort of better performance, let's say or to get beyond exponential, you have to be able to have lots of memory and be able to store link level bell pairs for long periods of time. Okay. If you do probabilistic swaps, then you could get by with a non-exponential decay by using nested scheduling. Okay, but exactly what you get is going to depend on like the level of multiplexing you have, the kind of coherence times you have, the frequency at which you can attempt to generate entanglement across the links. Okay, and it's useful to remember in the classical world that you can get constant rate. Okay, and so there's a question of can we get anywhere close to that in the quantum world? Okay, so I'm going to show you a different way that you could imagine doing routing, and I'm going to do it in the context of a two-dimensional grid network. Okay, where Alice is positioned in one of the internal nodes, and Bob is a corner node here. The probability of successfully generating entanglement across a link is P. And so we're going to assume time is slotted, and during one time slot, you generate link level entanglement, and then you swap. And you can just continue to do this. But if you don't use a link level entanglement at the end of a slot, then you lose it. Okay. We have 1 qubit per link per router. And we'll assume that swaps are probabilistic. They succeed with probability Q. Okay. And as I said before, the memory holds states for just one slot. And so what we're going to do is we're going to route through, or allow Alice to route across multiple paths to Bob. So for example, let's say in one time slot, we generate link entanglement across this upper path from Alice to Bob, and then a lower path from Alice to Bob. Then what we will do is we will use both of those, and we will now attempt the swaps, which are probabilistic with probability Q. And the success probability then is that we're going to, per path is going to be just the probability that we successfully generate, the success probability, P sub L, is going to be proportional to the probability that we successfully swap at all of the intermediate switches. Okay. Now, in order to do this, we require global knowledge. Okay. And so if you analyze the performance of this, you see the following. Below, I'm showing two 3D plots with this 2D grid, I'm sort of have the distance between Alice and Bob on, let's say, in terms of the x-axis and also the y-axis. And we're looking at the log of the entanglement rate. And we're looking at two settings. We're going to assume that swaps are deterministic. Q is equal to 1. You always succeed. And in the top surface, the link level entanglement probability is 0.55. And in the bottom surface, I've decreased it to 0.45. And what you notice is that the entanglement rate doesn't depend on how far apart Alice and Bob are in the case of a link success probability of 0.55, but when it goes down to 0.45, it decreases exponentially. And that can be explained by percolation theory. And what happens is that there's a threshold such that if the link level entanglement probability success is larger than that threshold, you end up getting distance independent rates, provided that the swaps always succeed. And if you're below that, you don't. Now, once you have probabilistic swaps, then you lose this sort of distance independence. In the right 3D plot, again, I'm showing as a function of the x and y distances, the log of the entanglement rate, what it looks like when swap probability is 0.9 and the link entanglement success probability is 0.6. The top surface corresponds to the case where you have global knowledge. The bottom surface corresponds to the case where you just pick the shortest path between Alice and Bob. And the one in between, it comes from using a local policy that tries to use all of the link level bell pairs that get generated and does sort of selects which ones to use depending on what it estimates is the distance between it and the two end nodes. Okay, and so it turns out that you can do, you can't get distance independence, but you can do much better than using a single path. And a question then arises whether it is possible to generate distance independent rates when you don't have deterministic swaps. And so that brings us to the following poll question. And what's the dependency between the distribution rate and the distance when swaps are always succeed and the probability of generating a link level entanglement is larger than this sort of percolation threshold? Does rate decay exponentially with distance? Or does it decay logarithmically, polynomially? Or do you get distance independence? Or, of course, the last is that I don't know. Okay, I'm waiting for a few more responses. Okay, well, we have more than a third of the responses. I'm going to turns out that the answer is that it's distance independent. Uh, Mateus,
Yes.
I noticed that at least in the pop-up, it's distance dependent, but that's not what we have on the slide.
Yes. Yes.
Uh, So it turns out that it is distance independent, and going back to the previous slide, it really corresponds to, let's say, this sort of illustration of the top surface, that when you have deterministic swaps and your link level entanglement success probability exceeds what's called the percolation threshold, then you get distance independence. Now, if you allow something more than just, let's say, bell pairs, so for example, we talked a little bit about GHZ states, and an n-qubit GHZ state you can think of as a generalization of a bell pair. And let's say you have a switch that has three or more link level bell pairs that were successfully generated. Then instead of just swapping pairs, you can do what's called a GHZ fusion on all of them. And that has the effect of generating a GHZ state. So here we have, let's say, three GHZ states, and let's say we have three qubits that we can perform a fusion on. And if it succeeds, then this will give us a 7 GHZ state. Okay. And if it fails, then things sort of fall apart. And so if, let's say, the probability of success is Q and probability is 1 minus Q, then it turns out that in this 2D grid, if we now allow the switches the capability of doing these GHZ fusion operations instead, then if the link level entanglement success probability is large enough and the swap probability is large enough, you can get percolation and you can get distance independent rate even when swaps are not deterministic. Okay. And it's interesting, this approach, if you know something about classical networks, is very much analogous to doing broadcast or multicast. Okay. And you can have sort of different protocols depending on exactly how you do the fusions. Okay, so that's all I want to say about routing. I'd like to now talk about a connectionless architecture for a two-way quantum network. Think of it that I want to show you a way that you can make it look as close to the classical internet as is possible with a two-way network. Okay, so what do I mean by this? What I would like is that the switches and repeaters have little or no flow state. We saw that typically what you might expect is you'd set up a path between Alice and Bob, and then use one of the scheduling policies on swap scheduling policies on that, and you'd have to maintain state so that you knew which flow you were essentially giving the link level entanglement to, and that you were doing the swaps for. Okay, so we'd like to get rid of that state, and we'd like to make it look as if each entanglement request is sort of being handled independent of the other entanglement requests. So let's look at those three policies that Mateus talked. We have swap ASAP. And if you think back to it, you really have to have all the switches synchronized so that they know what flow or what end-to-end pair they are generating or doing swaps for. Nested swapping, again, it's the same thing. If you think back to what it looked like, you really need to have tight synchronization among all of the nodes on the path. Okay, and that's what we would like to avoid. On the other hand, what's nice about the sequential swapping is that that's not needed, that you give link resources to a flow only when some request belonging to that flow asks for them. Okay. And it only requires link level synchronization, and I'll sort of go through that. And so that makes this analogous to the datagram service that sort of underlies the classical internet. Okay, so what are sort of the advantages of this? Well, we simplify synchronization. It turns out that when you think of like the classical communication exchanges that need to take place, they're pretty complicated in swap ASAP and nested, but with sequential, it's really link by link. Another nice thing that we're not going to get into is it turns out that it's amenable to doing very simple mathematical analysis, which is always good for understandability and for network management. And it really allows us to deploy classical internet protocols, let's say from the network layer up. TCP is the sort of the predominant transport protocol. Well, you can have a quantum TCP that looks very much like that. Destination-based routing is predominant in the classical internet. It turns out that this architecture is going to allow doing that if you so please. Multicast is sort of a service that the classical internet provides that allows the transmission of data to multiple receivers. And it turns out that many of the ideas for classical multicast can be used for doing multipartite state distribution. Let's say for the distribution of GHZ states. Okay, so basically we're going to take sort of a packet switching paradigm, and if we sort of look at the TCP IP network stack, we're going to see how we can map that into this connectionless architecture. And what it will allow is using very simple statistical multiplexing to share the resources among multiple users. And this, was fundamental for the internet performance. Okay, so here is the quantum protocol stack. As Mateus mentioned earlier, you have a transport layer, and here what we're going to see, we're going to have a quantum TCP that will reside here. Below that is a network layer that's concerned with end-to-end bell pairs, and this is going to correspond to the connectionless architecture that we're going to do sequential swapping coupled with store and forward, and then with some routing protocol to decide where we forward, let's say, a bell pair request. And at the link layer, the assumption is that we have some sort of heralded link level entanglement generation, and there's a link controller, let's say, associated with each link. And the physical layer, it's basically quantum operations in the switches and for transferring qubits from memory qubits to photons that go across the links. So let's look at the link layer. We're going to have heralded link level entanglement generation, and it could be multiplexed. And basically, nodes are going to request entanglement from the controller. The controller is going to orchestrate the generation and decide which link to give it to. And in this connectionless architecture, we're going to have these requests. They'll have some sort of ID associated with them and a link level label. And we can do distillation at link level and across segments of links. And this link level generated entanglement links will now be available for the network layer to consume. Okay, so let's look at the network layer. What it's going to do is it's going to forward Bell states like packets via sequential entanglement swapping. Okay, we're going to have a quantum datagram, and it's going to consist of a Bell pair, and then a bunch of classical data that, let's say, might identify the destination and let's say the initiator of the Bell pairs. Maybe it will include information regarding how long this request has been in the network as a way of allowing routers to sort of determine what the fidelity of the Bell pair might be. There are any number of things. So we have our initiator on the right. It has a request, and as soon as the first link generates a Bell pair, the request moves to the first repeater, and there it sits until a link level Bell pair is created across the next link. You do Bell state measurement, and then the request moves to the next repeater and continues like that until we finally end up generating an end-to-end Bell pair. Okay. And notice there's no need for resource reservation. And what you really have is sort of best effort service here. Haven't said anything about how you allocate the link level Bell pairs among the different requests at the node. But yeah, you could imagine any number of types of schedulers. You could give differentiated service to different flows. You could have priority scheduling if you wanted. That all of that is supported. Let's look at the transport layer, and let's say a quantum TCP. And you could imagine it then it'd be TCP-like with an opening handshake, let's say data flow, which is really the flow of these requests, and then acts for the delivered quantum datagrams. And one thing that this QTCP would do is control the end-to-end quantum datagram rate, and which is analogous to congestion control that TCP performs using what's referred to as an additive increase, multiplicative decrease algorithm. And you could include what we refer to as an active queue management algorithm at each router, which would essentially impose sort of a soft cutoff on the time that a request spends there as a way of reducing memory decoherence. And here I'm showing a graph. It's a plot of fidelity for different flows in a small regional quantum network. And we're showing two curves. I've essentially ordered the flows in decreasing order of the fidelity that they receive. The orange corresponds to this proposed quantum TCP, QTCP. And there's another algorithm here called AQTP in blue, and it is a reservation-based algorithm. It operates by reserving memories at the various routers for each flow. So the orange one is connectionless. The green one, if you want, you can think of it as a virtual circuit oriented protocol. And what you find is that by going connectionless, you can get many more flows at higher fidelities. Okay, so poll question associated with this is, what are the benefits of a connectionless quantum network architecture? A, requires minimal synchronization. B, reduces total amount of required classical communication. C, permits borrowing ideas from the classical internet for application to the quantum network. D, provides distance-independent entanglement rates. And the answer is that it really simplifies the problem of synchronization and minimizes it. And one of the benefits of it is that it really allows one to just take whatever they want from the classical internet. There's a caveat there. There are certainly, tens of thousands, hundreds of thousands of ideas, protocols, algorithms that have been developed for the classical internet. Many of them are bad, and so one of the things that we or you will need to be careful about is that you borrow good ideas and not bad ideas. Okay, and so I'm going to stop here, and I'm going to turn it over to Mateos, who is going to cover the last section on quantum network tomography.
Thank you, Don. Should we go right ahead, or should we have another 5-minute break, Don?
Well, we can take a 5-minute break.
Okay.
What time is it? So 20 minutes till the hour?
Yes. Yeah, I guess there's only one open question in the Q&A section. That is if you can perform teleportation using GHZ states. And if yes, what is the process? To be honest, I'm not sure. I think there are some protocols that do something like teleportation, but it's not like the way that we saw how teleportation worked for Bell states.
Yeah, well, so you certainly can do teleport from Alice to Bob, because you can always transform a GHZ state into a Bell state.
Yes.
I don't, and you could teleport from Alice to Bob and Charlie, but those states will be entangled.
Yes.
Uh,
But I think that if you want to herald the state at the
uh,
the
you would have to send the measurement results
uh,
to both Bob and Charlie.
mhm, mhm.
But what I don't have a sense of is how useful the entangled states of Bob and Charlie are.
Mhm.
Uh, Quantum fluctuations. I guess I don't know what quantum fluctuations are. Do you?
I don't.
I guess we don't know what vacuum fluctuations are either.
Yes. To be honest, I don't know. Oh yeah, there's a poll question that is why is it not a poll question, sorry, a question that's why is it called connectionless? And the reason is because a connection-oriented architecture is something like circuit switching, where first you try to establish connection between end nodes, where you reserve resources, you allocate resources even before you start communication. And connectionless is when you do something like packet switching, where there's no notion of a pre-allocation of resources and the creation of an actual physical connection between the two end nodes, or even virtual connection between them. Okay, so maybe we should start then or resume. It's already
Okay.
3:40. Oh,
Yeah.
or my time, I guess 1:40 your time. Yeah, I guess you can see. Yeah, I guess you can all see the screen. And then, as Don said, this is going to be the last topic we're going to talk about today, which is quantum network tomography. And let's start with a very simplistic outline of the things we're going to see. First, we're going to talk about management and tomography and give you an overview of what we mean by performing network management and tomography. And then we're going to dive deeper into how classical network tomography works, and then migrate to quantum network tomography. And then we're going to see a way that we can perform the characterization of star networks or quantum networks that have the shape of a star utilizing quantum network tomography techniques. So network management really is a field that deals with the collection of data from network components that can be used to aid decision making in terms of the network managers. It can be utilized to detect fault hardware and software in the network, and also allows us to determine traffic patterns among different user groups or different user pairs. And network tomography is essentially a set of tools that have the goal of inferring the internal behavior of the network by only looking from an external view or from the perspective of external nodes. And what this means in practice is that we want to estimate error parameters for internal components of a network utilizing end-to-end measurements. There is a typo here. This should be end-to-end measurements. And what we want to achieve is what we call identifiability, which is how can we actually obtain a single value for the parameters characterizing the internal components of the network from a set of end-to-end observations. And why would we like to do this in an end-to-end way? Well, first, we would require minimum or no participation by the network to perform inference. The measurements in the case of classical networks will simply be packets that are exchanged among or between end users. We won't require any sort of administrative access to the internal components, meaning you don't need to log into or access a router to perform measurements. We can perform inference across multiple internet domains, such that we don't require a lot of cooperation between different domains, and also can be used to monitor service level agreements. So if you recall, we saw that different ISPs have treat each other as customers and providers. And then one thing that you could essentially do is to try to come up with ways to monitor whether or not the service level agreements are being held. And then finally, one thing that is quite interesting is that when you perform end-to-end estimation and when the end nodes have access to characteristics or parameters characterizing the network components, you have essentially reconfigurable end applications such as video and audio streaming, or even performing things such as reliable multicast. Okay, so let's go over a quick poll question now. Why is end-to-end estimation interesting? We have A, it does not require administrative access. B, it yields reconfigurable applications. C, does not require trust in the infrastructure. D, all of the above. Or E, I don't know. Oh, oops, sorry. I think I... Yes, I guess. Maybe you can wait a little bit more to see if we have a more than 50% participation. Okay, so let's see the answer. Actually, all of the above are correct. All of A, B, and C are interesting points or reasons why we would like to perform end-to-end estimation in a network. So in order for us to start talking about classical network tomography, let's see some definitions. The main focus or the main metrics that are interested in estimating are link level metrics, such as the communication delay introduced in a link or the loss probability of sending a packet through a link or bits between neighboring nodes or the bit flip rate, meaning what is the probability that if you send a bit 0 between A and B, starting at A, B receives a 1, so on and so forth. And then we will see methods for tomography that rely on unicast communication. Unicast communication is a one-to-one paradigm of communication where if, let's say, A wants to send a message to B, it will send that message first to S, and then S will propagate that message to B, and this constitutes a one-to-one communication between A and B. And if A wants to send a message to C, even if it is the same message that it wanted to send to B, it will repeat this process, sending the message again to S, and then S propagates that message to C. The second way that we can perform communication is multicast, and multicast is a paradigm of communication where we have a one-to-many. Now let's say that A wants to send a message to B and C, and this is the same message. So what A does is that it sends this message to S. S duplicates the message. It sends one copy to B and another copy to C. And what is important to note here is that S is actually the node that duplicates the message. And the message, which is the same that is transmitted to B and C, only passes through the link interconnecting A and the switch, or S in this case, once. And then what we mean by estimation is we're going to perform many rounds of communication among the end nodes, either in unicast or multicast, and perform our measurements. And what we do is that the end nodes will collect all of the measurement results and send it to a data fusion in the network so that the data fusion can calculate or solve the estimation problem that we are interested in. The first procedure we're going to see is how we perform unicast tomography. We have some assumptions here. We're going to assume that the metrics on the links, the ones that we're interested in estimating, are symmetric, meaning, let's say, the delay introduced when you send a packet from A to the switch is R0, and that's also the delay if you send a message from the switch to A. And then we have additive metrics, meaning that if we send a packet from A to B, the delay that is perceived by B is the sum of the delays introduced by the individual links that the packet goes through. And the way we're going to perform tomography is as follows. We're going to define end-to-end measurements as measuring the total time. Let's imagine that we're looking at delay for now. The total time that takes to propagate a message from A to B, and then which is, as I said, additive, is nothing more than the sum of the time it takes from the packet to propagate over this link and then over this link. And we're going to look also at the time that we have that it takes to send a message from A to C, which is the sum of R0 and R2 in this case. And finally, we have the time it takes to send a message from B to C, which is R1 and R2. And if we look closely to these measurements, here, the results are on the left, we actually have a linear system that connects the perceived observed behavior end-to-end with the individual metrics we want to estimate. And we call this sort of a set of measurements as a routing matrix because it is simply telling us, describing the links that we utilize to perform our measurements. And if we do so, it turns out that if we can invert this matrix and we have linear independence in our measurements, we can actually identify values for R0, R1, and R2 given that we can only measure R sub AB, R sub AC, and R sub BC. And this is true not only for a switch like this, but for general trees and in fact, general graphs. If you can come up with routing matrices interconnecting end nodes that are invertible, you have identifiability for your the link parameters we're interested in. One thing that we can also do is actually to perform measurements over cycles to try to overcome some of the assumptions of symmetry in the links. But the key idea here is really to focus on the fact that we can come up with a matrix that is called a routing matrix that determines the paths that will be utilized to probe our network, the end-to-end measurements. And then whenever that matrix is invertible, we have identifiability for our metrics. So let's go over a quick poll here. What is a sufficient condition for link identifiability through unicast tomography? A, link symmetry. A, link asymmetry. B, link symmetry. C, the invertibility of routing matrix. D, having a network with star topology. Or E, I don't know. I guess maybe you can see the answer now. So I guess most of you got it right. The sufficient condition is the invertibility of the routing matrix. As long as the routing matrix is invertible, we have identifiability for the case of additive metrics. Now let's see how multicast tomography works. Let's imagine that we have a network here shown in this figure of 3 end nodes interconnected by a switch, and is again a tree. And this is the source of the messages, or the communication source, and these 2 end nodes here are receivers. The multicast probes are, again, probes that are, where the copies of the messages that are required to send information from the source to the receiver are only performed when they are needed. And essentially, multicast works via trees of the network. So it turns out that the fact that copies are only created when they are necessary introduces some correlated performance that is observed by the receivers. And what we want to do is really to exploit this correlation to be able to infer properties of the links, such as rates and delays. And now what we're going to look at is how we can, to see how this sort of correlation appears when we're looking at the loss rates introduced by each link in the network. Let's imagine that we have probabilities for each one of the links for successfully transmitting, let's say, a packet or a bit. And let's see what happens as we try to send information from the source to the receivers. So if everything goes well, the message from the source succeeds in traversing all of the links, and then both receivers get a message, the message. If we have a loss on the link on the left and a success on the link on the right here, we know for sure that the message was successfully transmitted from the source to the switch. This is also true when we see the opposite scenario, where we have a loss on the right link and a success on the left link. And we can actually record the number of times you see messages on both receivers or on only one of the receivers, and use this data to estimate both all of the probabilities for loss in the links of these trees. So again, let's go over a quick poll concerning multicast tomography. What is the key principle behind identifiability in multicast tomography? A, measurement correlation in common links in the multicast tree. B, invertibility of the routing matrix. C, symmetry in the links. Link symmetry. D, link asymmetry. And E, I don't know. Okay, I guess we're almost. Yeah, okay, I guess that's a good time now to see the result. Most of you actually got it right again. The the key principle is the correlation, the measurement correlation introduced by common links in the multicast tree. Now that we saw how classical network tomography works, we're going to see how quantum network tomography does. So we can imagine that a quantum network will be formed by many different quantum hardware. For instance, we have end nodes that can be interconnected together via satellites and in ground stations. And the links between ground stations, between two ground stations, may have very different properties than the links interconnecting a ground station to a satellite and then a satellite to another satellite. And the key question we want to answer is, how can we characterize the links in a quantum network performing end-to-end measurements? In the setting, the end nodes are assumed to be able to perform quantum circuits. They can request a service of state distribution, and they can specify particular circuits, quantum circuits, to be executed in the intermediate nodes of the network. And the intermediate nodes are assumed to be able to receive requests for quantum circuits. They have access to some ancilla qubits, but they are not allowed to be utilized for measurements if these measurements are solely for the purpose of estimating the links. And the motivation why we want to do this is, well, we might have quantum networks with inhomogeneous quantum hardware where the performance or the noise introduced by each one of the links in the network differs drastically. We might have hybrid communication media. As I said, we can have networks that are formed by ground stations and satellites, and we would still want to be able to do some sort of network management within quantum networks. So we would like to be able to detect where faulty hardware in the network, and also get information to perform decision making, such as how to better utilize resources. Let's say how to perform routing when we have links with different performance. Another interesting application here is to perform noise-informed quantum error correction, having the descriptions for the noise profile of the links and of the end-to-end noise can be very helpful when decoding information from quantum error correction codes. And in fact, you can see an increase in efficiency given that you know properties of the noise that is acting on qubits. Another interesting feature that could be done with end-to-end estimation is quality assurance. For instance, how can you know that the quality of quantum information that you're paying for your quantum internet service provider is actually the one that you're receiving? And being able to perform network tomography would allow you to answer this question. And finally, you can also have some sort of reconfigurable applications in the end-to-end node, in the end nodes, that would change its behavior depending on how the state of the current state of the network is. So now let's see how we're going to pass from classical to quantum. In classical, we had link level metrics, and in quantum, we have parameters that characterize the quantum channels. We had probes in the classical domain that were essentially packets, and in quantum, we're going to perform quantum state distribution among n nodes. Unicast methods in classical gets translated to bipartite state distribution in quantum, while multicast methods in classical translates to multipartite state distribution in quantum. Finally, end-to-end measurements in classical become quantum measurements performed in the n nodes in the quantum domain. Our operation assumptions, once more, are that we have n nodes in the network that can perform quantum circuits. They can request a network to distribute states for them, and they can not only request, but specify particular circuits for the intermediate nodes in the network that are going to be executed to distribute these states. And then the intermediate nodes receive requests for quantum circuits for distribution. They have access to ancilla qubits, but they are not allowed to perform measurements for estimation directly. Our network models is as follows. Again, we model the network as a graph where the vertices of this graph are quantum processors. They can be routers, quantum switches, quantum repeaters, or quantum computers even. And the edges of these graph are denoting fiber optics or free space channels that enable the nodes to perform quantum communication with each other. We have n nodes in the network, which here we see as nodes A, B, C, D, and E. And then we have intermediate nodes, in this case, F, L, K, and J. And we're going to assume that each link in this network is a single qubit quantum channel. And for now, we're going to focus on one-way quantum transmission, where we directly send qubits through the channels. Okay, so in particular, we're just going to focus on the case where each one of the links is a Pauli channel that has its operator sum representation shown here in this equation. And it doesn't matter much what it is now. The key property here is that a Pauli channel is characterized, a single qubit Pauli channel is characterized by 3 real parameters. Our goal is then to estimate the parameters that characterize each one of the Pauli channels corresponding to the links of the network, performing only measurements for estimation at the end nodes of the network. This is the general setup for quantum tomography, and the method that we're going to learn today is how we can characterize networks that have a star shape and where each link of these network corresponds to a bit flip channel. So let's look at this simple scenario here of a star network with 4 nodes, and each link is the bit flip channel that has a operator sum representation shown here by this equation, where we only have one parameter that we must specify in order to characterize the bit flip channel, which is the bit flip probability. So there is a typo here. This should be E of rho. This should receive rho as input here. But the one way that we can look at this equation is that if we send rho over the channel E with probability theta sub E, nothing happens to that qubit or to that state. And with probability 1 minus theta sub E, we apply a bit flip operation into that state and we get a bit flip error. This means that we are mapping the state 0 to 1 with probability theta sub 1 minus theta sub E. Sorry, this is another typo. And we map again the state 1 to 0 with probability 1 minus theta sub E. So there's a typo here. This should really be 1 minus theta sub E. And the type of entanglement of state distribution that we're going to use, or the probe, is called the independent encoding probe. And it looks a little bit like this. So we're going to start by looking at node V0, which is this red node. And this node will prepare a Bell state, 0, 0 plus 1, 1, in these 2 qubits. Then it will send one of these qubits through E0 to the intermediate node V3, which is the gray node. And in the qubit that it's still stored in its memory, it will perform this quantum gate at x, h, x, and the qubit that is received by the switch will undergo a transformation of the type ZHZ. So this is a quantum gate. This is simply applying the Pauli gate Z, the Hadamard gate, and the Pauli gate Z again in the qubit that it was received by the switch. Then a C naught is performed in the intermediate node, controlled by the qubit that it was received, with a new ancilla qubit initialized in state 0. The result of these operation is a 2-qubit state where 1 qubit is sent through E1 to link to the end node V1, and the other qubit is sent via link E2 to the end node E2 to the end node V2. Then whenever we perform this, we finish these operations, we will perform measurements in the end nodes in the qubits that were received. So if we assume that we have pre-shared entanglement, in particular pre-shared GHZ states, we can perform a GHZ or even Bell states. We can perform a GHZ measurement in the 3 nodes that and the 3 qubits that we have that are not anymore located in a single node. And if we have so, it turns out that the bits that tells us about the measurement outcomes actually tells us whether or not a bit flip occurred in each one of these links. Meaning that if you look at this, the outcome of this measurement here, shown in the red circle, if it was 1, we see there was a bit flip occurring in the first link. If this measurement gives you a result of 1, you saw a bit flip in this link. And then finally, if you had a measurement of value 1 in this end node, you saw a bit flip error in this link, E2. We can actually characterize more complex networks utilizing this star approach. And the idea is that we're going to come up with virtual stars that are going to cover our entire network and utilize correlations between the outputs or the metrics in order to characterize links whenever we have complex networks. So one thing we can do is that let's look at these different stars here where I'm calling virtual stars, in particular trees, where we select trees within the network graph, not one, but many, such that at least each edge of the graph is covered by a tree. We will characterize these trees and then utilize the characterization for each one of the trees to somehow triangulate the parameters for each one of the links. And this is still an active area of research on how we can actually characterize big and complex networks or networks with complex topology in an end-to-end way. And there are some challenges. One very difficult question that we were not even able to answer for stars is, what is the actual optimal estimation strategy to characterize stars? How can we have optimal estimation or efficient estimation for arbitrary trees? How should we partition networks in trees to estimate all the links of the network in an efficient way? What is the difference between performing bipartite and multipartite methods? I haven't talked about bipartite quantum tomography, but there is a way you can perform tomography utilizing only bipartite communication and not multipartite. Under which conditions we'll see some advantage in estimating the network parameters with entanglement. Under which condition we can actually identify tree networks, and how to generalize, for instance, the methods that I showed you for bit flips to arbitrary Pauli channels. And with this, we finalize the our discussion on quantum network tomography, and let's go over a quick recap of everything that we saw in this course. We started with the discussion of the fundamentals of quantum communications, where we saw things such as the definition of a Bell state, of a GHZ state, of quantum teleportation, and we moved to a comparison between classical and quantum networks, where we saw how is the structure of the classical internet and how some of the design choices were made, what are some of the protocols that are utilized, and how they transfer or if they transfer or not transfer to quantum networks, and what are the new problems that are introduced whenever we look at the quantum domain. Then we discussed scheduling in repeater chains, which is essentially how we perform entanglement swapping when we have many repeaters. And we looked at what are the differences in performance when we utilize the three scheduling policies that we discussed. Then we we haven't actually talked about the capacity of networks. We talked about routing in quantum networks, where when can we utilize the same ideas from classical in quantum, and also some new routing methods that came exclusively from the properties of quantum information. And we pivoted to discussing connectionless quantum networks, and in particular an architecture to implement connectionless two-way quantum communication. And then the last topic that we discussed was quantum network tomography, which essentially deals with the inference of link parameters for quantum networks, where we're only allowed to perform measurements at the end nodes for estimation. And with this, I guess we finish our technical discussion. And I guess we'd like to thank you all for participating and for your time and engaging with us with all the questions. And yeah, it was quite a great time.
Yeah, I want to say the same thing, and we hope that you learned, got something out of this, and that you'll be interested in learning more about quantum networks.
I guess maybe I can stop sharing.
Yeah,
Yes.
and Mateus, there's one question that curious whether you might be able to answer it. One open question.
Yeah, I think one good resource is I think someone else asked us to share the challenge page. I'm just gonna share it again and leave it there as I address the other question. Okay. Yeah. Let me just I guess maybe I can stop sharing now.
Sure.
Wonderful. If we wanted to take do you guys have another moment or two to answer any other questions? If you have any questions, please make sure you put them in the Q&A. And then as a reminder, as we wrap up, there will be a post-course survey that we ask you to take just to give us your feedback. And the slides and course resources can be found on the website where you completed the registration. We'll also get those sent out separately in an email.
Mateus, we have one person with a hand up.
Oh. What should we do?
I just unmuted. Okay. Okay, well, I guess if there are no other questions, thanks again for attending.
Great, thank you both.